We continue now with a different part of TOPCon. So we had now 3 module manufacturers talking about their developments and strategies, and we look a little bit from a different angle at TOPCon. We are very happy to have with us now Laurent Clochard, who's the CTO at Nines Photovoltaics, a Europe-based equipment manufacturer, and he will delve into atmospheric dry etching for TOPCon solar cells. Laurent, the floor is yours.
Thank you, Michael. Can you hear me okay, yeah?
Yeah.
Excellent. Share my screen. Okay. Can you see my presentation?
Yeah, very well.
Is it in presentation mode? Because I'm not seeing the presentation.
Not yet. No. It's
okay. Now.
Do not.
Okay, that should be okay now.
Yep.
Very good. Thank you for this opportunity, Michael, to present this new technology we're trying to bring to market. So I'm Laurent Clochard, the CTO of Nines Photovoltaics, and I'm going to talk about atmospheric dry etching for TOPCon solar cells. The outline of my presentation, I'll do a short company introduction, and then I will present the AD process and the tools that we have developed. We will then go through the TOPCon process etching requirements and the results that we've had so far. I'll talk a little bit about the roadmap, and finally I'll show you our industrial tool. So we're an SME. Founded in 2010. We are a European equipment manufacturer, and we do a lot of development, process development, and we are based in Dublin, Ireland. So our main focus is on atmospheric processing, targeting the PV market. We've been financed through private investments and also EU funds. In particular, we got great support from the EIT and Energy. A quick timeline about our development. So in 2010, we came up with our first AD proof of concept. In 2016, we built our first tool, and Fraunhofer ISE were an early adopter, and they bought our first tool. At the time, we were mostly focusing on texturing, targeted for the multicrystalline market. In 2017, we set up our own pilot line here in Dublin with our R&D tool, and we subsequently secured funding and a partnership with a tool builder to develop our first multi-lane industrial tool. And in 2020, we have focused very much our process on TOPCon applications. And this year, the industrial tool was, our first industrial tool has been delivered, and it's going through testing at the moment. And we're targeting to have an official product release early next year. So in terms of application for the AD technology, we're obviously very much focused on the solar market at the moment. But we're looking at any sort of silicon etching application. So there are other areas we're also looking at and trying to find out some applications. Okay, so in terms of the ADE process, it's an etching process. Typically divide the silicon etching technology into either wet processes or dry processes. You're all familiar with the wet processes, that is the incumbent technology currently in the industry. In terms of dry etching, and other people are more familiar with the physical dry etch, which is typically reactive ion etching using vacuum and a plasma, and essentially the other category in the dry etching is chemical etching, and this is where the ADE process falls in. Okay, so in a nutshell, what is the ADE process? It's a silicon etching process, and it's purely a thermal process, and we're using molecular fluorine gas F2 to carry out the etching. The tool is an inline tool with a continuous flow of wafers. As you can see on the schematic, the wafers are passing through an open reactor, and they are held onto a belt, a conveyor belt. It's a continuous flow, and the gases are contained inside the reactor through PERC curtains. And there is no vacuum. It's entirely at atmospheric pressure. And there is no plasma or ions in the process. It's purely a chemical etching. And the fact that we have no need for vacuum or plasma, these are obviously the main cost drivers of technologies like reactive ion etching. And we have essentially removed all those cost drivers for delivering a tool that's a lot more economical and applied to the requirements of the PV market. So this is what the actual reactor looks like. This is a picture of our R&D unit. That's the one based currently in Dublin. You can see it's very compact. The length of the reactor is about 5 wafers. This one is a single lane. It's just for pilot line and R&D application, but you can already get a pretty good throughput out of it. And you can see the belt also where the wafer stand. So we're using, typically we're using in our setup diluted F2 in gas cylinders, typically up to 30%. The main process advantages of the ADE are a very high silicon etch rate. It's also a single-sided process, and it provides a very selective etching versus dielectric layers commonly used in the industry like silicon oxide or silicon nitride. And it's also a relatively low temperature process, so we're talking about around 200 degrees. So in terms of industrial process suitability, it delivers a very high throughput. And because it's a gaseous process, we get a very good process control through MFCs and very good stability. And the footprint of the tool is very small, as you've seen before. And the other very good advantages in terms of industrial application is that at scale, you can deliver a very low cost of ownership through the use of on-site gas generation for the etching gas. And that's something I will come back again a little later. But also very important, obviously no DI water, no water use for such a process. We're completely dry. And there is no greenhouse gases involved in the chemistry, despite the fact that you might relate fluorine to a fluorinated compound. F2 molecular fluorine and a zero global warming potential. So no greenhouse gas. So this is a picture of the R&D pilot line, and You can see it's a very compact setup. We're talking of a width of about 2 meters, and this picture actually includes the loader, the loading and unloading part of the equipment. And typically we use 100 wafer cassettes. This is the tool that Fraunhofer ISE purchased a while ago, and this is the tool they're still using at the moment. So it's also a single lane reactor. It's a little bit different to the one that we have, but it's actually very similar. And fully automated, it's loading and unloading, and this is what they use in their current process for TOPCon also. In terms of setting up such a tool in a pilot line or R&D facilities, it's a pretty easy setup. All you need is essentially a gas cabinet to store the F2 and 2 cylinders, and to scrub the exhaust gas. You can use a point of use passive dry scrubber. F2 effluents can also scrub through a wet process if you have that already in your facilities. Okay, moving on to TOPCon requirements more specifically. So we're looking at single side polysilicon wraparound etching. So as been mentioned before, most of the deposition methods, current deposition methods lead to partial or full parasitic wraparound. And the type of wraparound that you're getting can be either a full wraparound or a partial wraparound, as displayed on the right side of the picture. And so you can see that the front side wraparound is mainly leading to absorption of incident light and losses, and that will impact directly the cell efficiency. But what's also happening with the wraparound is it goes around the edges and leads to formation of shunts. And in that case, you're affecting directly the module reliability. So it's very crucial to remove not only the front, but also what's around the edges. So this is what the wraparound looks like. On the left side, different types of wraparound, I suppose. A collection here on the left side of a full side coating of amorphous silicon. So you can see the pink color comes from the oxide or the BAG layer that's still underneath. And then on the right side, 3 levels of partial wraparound around the edges of the wafers, depending on the technology and the process being used in the deposition. So it can be quite wide, narrow, or extremely tight around the edges, but it still needs to be removed. Here's the typical process, TOPCon process we've been using with our partners at Fraunhofer. And you can see that after the LPCVD, so you get a symmetrically coated wafer, and you can see on the right side here the SEM with the BAG layer underneath the amorphous silicon. So this is before the AD process, and after the AD process, you can see it has been fully removed. And the BAG layer has been untouched because of the high selectivity of our process. So it etches the silicon much faster than any oxide or glass layer. Here's the analysis of one of the batches. And that's a thermal analysis looking for hotspots, and you can see this is clear from hotspot. And this one was measured with reverse current less than 1 amp, and the batch was with cell efficiencies more than 23, between 23 and 23.8%. So all the shunts are removed, which meets the module requirements, which are very important because the hotspots will create a lot of damage at the module level, not necessarily affecting the cell performance for the cell on its own, but once it's in the module and in real world condition, that's a different story. So these are the results that were compiled by the team at Fraunhofer ISE and Dr. Vishnu Kafler. That was published during the last EU PVSec. And that's a compilation of the reverse currents for a number of batches on a number of different settings, and you can see the results are consistently very low, and it's a very low reverse currents, which is what you're looking for. This batch was done with a full phase wraparound, so we removed the whole. The wafers we started with was from an LPCVD batch, and we had to remove the whole amorphous silicon layer on the top. This is also work from the team at Fraunhofer, where they've been looking at the etch wraparound this time, so how much of the etch is going under the wafer, because in order to clear that edge, you always have a little bit of gas going at the bottom, and they do some SEM analysis, and you can see when you move away from the wafer edge, so there's about 5 micrometers distance where the polysilicon has been removed, and then it starts to go again slowly from about 500 micrometers. Okay, so in terms of summary of those results, we got a very good selectivity when we do the etching with the ADE process, which, I mean, the BHG layer are untouched, which provides some sort of flexibility on the BHG's thickness that you can use, and on the diffusion process that you can use. And by the way, you could have any other underlayer, dielectric underlayer, that would work pretty much as good as this. We have shown results as well with all type of polysilicon, whether doped or undoped, annealed or not. And the wraparound was about less than 500 micrometers from the edges. The edges are fully etched, and we got parallel, very good parallel resistance of 500 centimeters square. And all that obtained with a pretty fast etch rate up to 12 micrometers per minute. Just a word about the roadmap, the way we see it here, from our perspective, I suppose. At the moment, the passivated contact are applied to the rear side only. And that's the main focus of the development. But the next logical step, as Radovan mentioned earlier on as well, is also the front side passivation, in order to get those extra efficiency points. And we think that will require some more intricate etching steps. And we feel that ADE could be very useful to do that, because of our etch selectivity and the fact that we have a single-sided process. So in terms of roadmap, we've been also talking about IBC, and in a similar way, back contact architecture could benefit from a technology like ADE, single-sided and selective. Another development we are still working on is the texturing process, although it's not our main focus at this moment. This is still something that we want to develop further. We have a patented process to generate inverted pyramids. So nanotexturing process, and hopefully we'll come up with some new results during next year. And finally, I want to show you our industrial product. So that's the new machine that we have developed and we're planning to market as an industrial machine. We've been developing the machine in partnership with an OEM builder that provide us with large capacity to manufacture those tools. This is called the AD3000, and you can see the inside here. This is a modular tool with a 3-lane conveyor. And you can see here easy access, automatic tracking of the belt, easy access for servicing. So this tool was very much designed with production in mind. And this is a sort of configuration that you can have for it, either a 3-lane system or coupled together a 6-lane system delivering some throughputs depending on the type of wafers you're using. As you can see, we can go up to 6 lanes and 12,000 wafers per hour for up to M4 wafers. And this is transformed into 4-lane systems for M6 to G12 wafers. In terms of fluorine supply versus capacity, depending on how much you're planning to use, there are different solutions for the supply. I mean, this is not something that we do, but this is just to give an overview. So for smaller capacity, you can use gas cylinders or gas bundles. For larger capacity, you can start to use on-site generation, and that's where you can bring your costs down. So you have either the choice of smaller generators, or if you're on purpose for multi-gigawatt capacity, then F2 plants make sense, and you get a very low cost of ownership to produce that etching gas. One last word about environmental impacts. I mean, obviously, when you select your technology, and considering that the PV industry expansion is very much on track and planned to expand quite dramatically, it's important to consider the implication of the technology that you're going to use. There's a growing importance of water footprint and pollutant and toxicity, and a special focus on greenhouse gases. So obviously the PV water footprint, the PV industry water footprint comes from the wet chemical processes. Our process is a dry process, and I think moving toward dry process would be a good thing. So this is maybe a first step forward we're proposing with our new technology. And as I said earlier on, despite using fluorine, the F2, which is molecular fluorine, has 0 global warming potential, so it's not a greenhouse gas. So no global warming impact. Okay, so this brings me to my conclusion. I've been presenting you with the technology we're trying to bring to market, a new technology for etching for the PV industry called ADE, Atmospheric Dry Etching. We've demonstrated some process results for TOPCon poly removal, which is our main application at the moment. We're working in relation with Fraunhofer ISE for this qualification. The tools we provide have a very low footprint and low cost of ownership at scale. And we feel the technology is relevant for upcoming cell technology and upcoming cell development. The process we're using is sustainable in terms of low water impact and no greenhouse gases used in the etching gas. Okay, so we hope we can contribute to the PV industry and move it further toward more sustainable processes. And if you have an interest in sampling and trying out our process that we're trying to bring to market now, please get in touch with us. Thank you very much.
Thanks, Laurent. Very great to see the news about this innovative tool. I think there were also a couple of questions or comments in the chat. So if you can answer them in written form, that would be very nice. I think we're in time. Let's continue